So starting this week, we're going to be talking about persistence and relational database management systems and SQL or SQL. So most of the programs you've written up until now have lacked any real method of persistence. That is to say, you've been writing to a CSV file, not a database. So this week, we're going to focus on writing programs that save their output by reading from and writing to what's called a relational database management system, or RDBMS. The other word you'll probably hear about this is a SQL database after the language, a structured query language that's commonly used to query a relational database. So let's talk about databases a bit. So before we jump into a new technology, let's ask ourselves, okay, is there a simpler option than just using a database? And you'll see that having an RDBMS, SQL, and Python together is no small feat. Like, what's another option we could do if we wanted to do something besides using a real database? There's something we've been doing all last week, right?
You can
Write to a CSV file.
Yeah, we could have a CSV file or some other sort of text file. One thing we could do is just have one file per student and name each one with their student school ID number. So I could do something, so let me start up real quick. So I'm going to open up this file here. So we could have a data folder, and inside of it we could have 321-531.json, which is another type of text file we will have access to. 934.894.json. So every student gets their own file, and each file might contain the student's entire school record. So I'm going to copy and paste something here. So JSON can look a lot like this. So here's all our students' data. First name is Megan, last name is Remy. Their birth date, their address, their classes, all of that is all stored in this one file that we could call 321.521.json. And that's not, like, if that's all we wanted to do, if all we wanted to do was be able to retrieve a student's record by their school ID, this persistence method could actually be really, really useful. And I'll kind of, so we can, if we wanted to access this, we could import the JSON library and, get the ID as input. Do our file name, get our file name by file name equals data.join, and then we get all of we essentially get the input, the ID.json, something like that. And then we could load it and then print everything out very nicely. And that would work pretty well. But we'd have to do a lot of work. Yes? Was somebody just about to ask a question? No? Okay. All right. So if we just wanted to print out everything that's like this, that would be pretty simple. But okay, let's say everything's in its own file. What if we wanted to find a student record by name instead of ID number? What if we wanted to search for Megan instead of the ID 321.521? Or list all of the students enrolled in a particular course, like all the students in CS 101? Or finding the number of students whose birthday is in June? So keeping everything in its own text file isn't very flexible. So it's a good case. There are uses for it. It's just cumbersome in other cases. And people found that this, as soon as software developers began to solve real-world problems, they found that this wasn't really tenable. This structure is what's called hierarchical and file-focused. Hierarchical because it's a bunch of nested data structures. And so people found something else called relational approaches, a relational approach. But what questions do you have about kind of this example I was doing before we move on? Okay, so the solution to this problem came in 1977 by a guy named E.F. Codd. I think Chris posted his paper in the Slack, I believe, a relational model of data for large shared data banks. And it's kind of the foundation of what we consider an RDBMS today. So some good quotes that he's got is, future users of large databanks must be protected from having to know how the data is organized in the machine or the internal representation. So to translate that, it means we need some flexible persistence mechanism that insulates users in our code from exactly how the data is stored. Essentially saying, okay, our users shouldn't have to know all of the ins and outs of how it's stored in order to get their data. Then some other quotes. Activities of users at terminals and most application programs should remain unaffected when the internal representation of data is changed, even when some aspects of the external representation are changed. Changes in data representation will often be needed as a result of changes in query, update, and report traffic and natural growth in types of stored information. Also, existing non-inferential formatted data systems provide users with tree-structured files or slightly more general network models of the data. In section 1, inadequacies of these models are discussed. So the translation of that is existing hierarchical tree approach, like this. That approach to persisting and organizing data isn't adequate. So the relational approach to our student record system means we store our data in tables with columns and row, much like an Excel file. And kind of like we were doing with CSVs. So each table stores a different type of record. So if we want to design a table, it might look like this. We'd have students, and the columns for that would be ID, first name, last name, birthday, and an address ID. And the reason it has an address ID is we'd want to have addresses be its own separate table. And that could have line 1, line 2, city, state, and zip code. And then we could have another table called classes. And that could just have the ID, the name, and how many credits it gives you. And then we'd have another table called enrollments. And the enrollments table, all we'd be doing is saying, okay, student number 1 is enrolled in class number 2. So we have student ID and class ID and the grade they received. So this is all going to make more sense after today and tomorrow. But the RDBMS approach here that we're modeling here, instead of being hierarchical, it's flat. So there are connections between rows and different tables. This right here, the address ID, this is what's called a foreign key. It's kind of a connection between this table and this table. But there isn't a fixed final form. We're able to retrieve records from one or more of these tables, mixing the data to fix the question we're trying to answer. And if we change a few things in each of these tables, it won't change the entire structure. Everything will still work more or less the same way. So by separating our records into different tables that only contain the fields of one type of record, we can avoid committing to any single structure. And so what makes RDBMSs so useful is that they're flexible. So what questions do you have about relational database management systems?
Noah, I guess we're probably going to learn more about it, but I did notice that every one of your little tables here has an ID except the address, that foreign key.
Yeah, Yeah, the ID should have
Oh, okay.
each yeah. So one thing you'll find in SQL and RDBMSs is that every record has its own unique identification.
Got it.
So
I was just wondering about that one, but
yeah, yeah. If this address didn't have an ID, then this foreign key would be useless.
okay. Thank you.
Thanks for pointing that out. Okay. Any other questions about why we use relational database management systems instead of individual JSON files? Okay. So I'm gonna something in the chat real quick. Oh, it's also snowing in the Gold Coast. Awesome.
That's absolutely.
All right. So, kind of showing some examples of how we would query this in SQL, and we'll talk more about SQL in just a second. So it looks something more like this. Instead of creating a whole bunch of methods, we would just say select all, that means all, from students, where last name equals Garvis. So this is some examples of SQL. So this would be find a student by name instead of ID number. If we wanted to list all students from a particular course, it might look something like this. Select all from students, and then we do something called left join enrollments on students.id equals a student ID equals student ID, where class ID is 4. So again, this may not make much sense now, and that's fine. It'll make more sense after today and tomorrow. These are just some examples. I'm going to put this on multiple lines. And so essentially this translates to give me all of the information from students and then kind of combine it with the enrollments table. And we're going to be saying get the students ID we're going to match students.id. So this ID to student ID in enrollments, where that enrollment has a class ID of 4. So again, we'll have more time to practice this later. These are just some examples. And if you wanted to find a student, the number of students whose birthday is in the next month, we could say something like find number of students whose birthday is in the next month. You might say select count from students where birthday is greater than or equal to 2020/01/01 and birthday is less than or equal to 2020/01/30. All right, so some other benefits you get from an RDBMS. So some of the modern ones, so some of the ones we'll be working with include Postgres and SQLite, but there's also MySQL, MS SQL, Oracle. They can do more than just store data. They also allow you to, they allow multiple users to create and update records at the same time, so our programs can scale. They also can validate records, preventing incomplete or bad data from entering a system. So for example, we could make sure that we don't want to enroll a student without a birthday. So the database wouldn't actually allow us to insert a new row into our table if it didn't have a birthday. So you can also do things like ensuring critical updates, like debiting one bank account only succeeds when crediting another also succeeds. So transactions and locking. And it's also doing, and most importantly, allows us to return records that match certain criteria. So allows us to filter and search, kind of like what we were doing here. So that's, again, this is just kind of a big introduction to why we use this particular management system. Any questions on that before we kind of dive into SQL itself?
So if you make something that stores data like this to a database, like a JavaScript or Python thing, are there like ethical considerations for storing the data in a database like?
Good question. So I don't know if I can't think of any ethical considerations for using a relational database rather than a hierarchical database, because all that really matters is what data you're storing and for what purpose. So ethically, yes, there are considerations you'd want to make before you store certain types of data. If you look at what's happening with Facebook in the last decade or so, I'm sure you'll be able to see a lot about, okay, what happens when we store too much data without really consideration of why we're storing it and for what purpose, and how secure it is as well. But I can't think of anything that's specific to a relational database.
Noah, I know at my last company, they were able to give access to certain data because the data is broken up into these different tables. It actually allows the company, the administrator, to sort of be more secure in who gets what access to what tables. And so it was safer this way than having everything in one big table that everyone has access to.
Yes, that's definitely true. Yeah, it allows you to kind of silo data, so you can, have access levels saying, okay, I want access to students and classes, but not addresses or something like that.
And generally speaking, when you're creating a relational database, you want your tables to be as small as possible with just the relevant data to whatever you're trying to use. So if you create a person, like a student, obviously a student has a first name, last name, birthday, and they also have an address, and they also have all kinds of information, but you want to break up those tables, just like Noah did, into smaller tables. So only the table has the very specific information about it.
Mm-hmm. All right. Keep the questions coming. I love them. Okay. So let's talk about SQL. Also better known as SQL. So RDBMSs have two halves. One is the storage mechanism, so tables, columns, and rows. And the other half is the query mechanism, which we call structured query language, or SQL. So when people talk about SQL databases, they're really talking about relational database management systems that happen to use a language called SQL. So here's an example of a table. We have students. Students have an ID, a first name, a last name, and whether or not they're on probation. So, yep, here's a table. Each of these is called a column. So ID is one column. And each entry is called a row. So each type, so columns, rows. So every time we add something new to our database, we're adding a new row, and that row consists of multiple columns. So every SQL database has what's called a schema, which is defined as a representation of a plan. So a database schema is the plan we're using to store our data. And a schema usually describes three things: table names, column names, and what type of data is being stored. Other parts include whether or not a column must have a value, null versus not null, foreign keys, indexes, etc. So designing a schema is another part of creating a database. And we'll talk later about, okay, how do you actually design a good schema? So tables are identified by name, And the SQL command to create a table is you'd say create table students, and then the column names, create table addresses, then the column names. While almost any name is valid, these are good naming conventions to follow. It should always be lowercase and be a plural noun. And it's also a very good practice to include a unique integer column named ID on every table you create. Some database systems won't allow you to not include an ID. It'll break if you don't. So always include an ID just in case. So they have table name examples. So if you want to store people, you might call it persons. You want to store purchase orders, you might call it purchase orders. And if you're trying to store how, every time a post is liked, you could call it likes. All right, what questions do you have about tables before we move on to columns? Okay. Each column has a name. Lowercase singular nouns or adjectives are usually a good create naming convention. So this is the full command for creating a table called students. So we would say create table students. Then we would say ID would be ID, which is an integer. First name is using something called varchar, which is essentially another word for a string. And you'd always say, okay, what's the maximum number of characters that would take? Which I think the highest value you can give it is 255 or maybe 260. So the first name and last name would both be varchars or strings. And on probation would be a Boolean. And then you always end every single SQL command with a semicolon. This isn't like JavaScript. It's not optional. There has to be a semicolon. So each column type has a data type, which determines what type of data it can hold. So yeah, like I just said, integer varchar is a fancy way of a string of up to 255 characters long. So in SQL, you have to say what type of data it is, and the first name column couldn't hold any other data type except for a string. If you tried to put an integer in there, it wouldn't work. If you tried to put a Boolean in there, it wouldn't work. Or it might work and just immediately convert it to a varchar. But like you couldn't put 255 into on probation because it has to be a Boolean. So there are many column types, and what they are can depend on the database system. But the most common ones are integers, decimals, varchars, text, which you use for longer strings up to 16 kilobytes, dates or timestamps. So a date is just a day, month, year, and a timestamp is the date and the time. So as you maintain software, it's expected that you'll create new classes and write new methods and refactor existing code. And you'll do this to the same to your database schema. So new features often require new tables and columns, or perhaps migrating existing data to a new schema. Existing columns can also be modified to hold new types of data.
Noah, question about the last slide you were just on. Were you saying that that dates are that's a pre-existing like data type or something? Yep. that is in a certain format, so you don't have to define the format or tell it what a date is if you call the column a date column?
Yeah, the date column is already knows it's a data type. It's expecting a very specific format. I think you can specify. There are ways of specifying, whether you want it as day, month, year, or month, day, year, anything like that. But you don't have to, convert it to a specific data type. It is just a data type existent within SQL.
Okay, thanks.
No problem.
Is there a way to like restrict the kind of, say, string that you want, like create your own parameters for a column type, like a regular expression or something?
Yes, you wouldn't use regular expressions. As you go through SQL, you'll learn that there are ways to specify, parameters behind each column. So you could say, give each varchar thing a minimum length, for example, or you could, say, let me think. Like I think, for example, so there's been somebody developed a method that would just say like you want it to be an email, and it would actually automatically check whether or not it's a properly, created email address, for example. So yeah, there are ways of changing the parameters to make sure that it's very specific about what you want. So changing a database schema often isn't cheap. It can often require coordination with code changes and or other tools. So for example, third-party analytics tools or an Excel formula run against the CSV export of a table. So for this reason, you want to take your time when designing a schema, meaning when you're designing your database, the keyword here is measure twice, cut once, because you'll be stuck with your schema choices for some time after you make them. So always think about your edge cases and the different directions your project might take you. And if you're convinced you wish you had a different schema, the time to make the change is now. Making the change will never be cheaper than today. So, if you have a massive existing schema and you realize that you want to split one table into two different tables, it's always better to think of that earlier than later. And think, well, maybe I should, maybe I shouldn't. Just do it now rather than wait. So single responsibility. Have we talked about this term before in class?
I think we were talking about it a lot when working on object orientation and the functions that go into each class.
Yes, good. So successful software is built from small modules that do one thing well. So the principle of single responsibility is saying that each method, each class should do one thing very, very well as opposed to many things okay. Or in the words of Ron Swanson, don't half-ass two things, whole-ass one thing. So as software developers, we want to avoid big classes, long methods, and long lines. We've learned that smaller is always better when it comes to software. And that same adage applies to storing data in an RDBMS. So large tables that store more than one record or model should be broken up into multiple tables. So this student table now has a first name, a last name, on gradation, address line 1, line 2, city, state, and zip code, when it's easier to break it up into students and addresses. And again, just like your code, you want your schemas to be dry, don't repeat yourself. So you wouldn't stand for repeating the same snippet of code half a dozen times. You should avoid repeating the same data in your database. Design your schema to avoid data duplication. So for example here, we have students and addresses, and the addresses also have the student's first name and last name. This schema isn't dry, it repeats itself. So if we wanted to fix that, we would use a foreign key. So, and like the other problem with this is if a student changes their name, so Tiana starts going by Eric, then we'd want to make sure that it updates everywhere, not everywhere. And so essentially, the alternative to this is using foreign keys. So Tiana's address 4 points to address number 4 in our address table. And if Tiana changes their name to Eric or whatever, then the address doesn't need to be updated because that address ID remains the same. And so usually your foreign key will usually be the primary ID of the other record. Sometimes it's not, but I would say 99 times out of 100, it's the primary ID column.
So Noah, do all tables have, except for like your master students table, have a foreign key that points to like a new ID? Or could you have a situation where like at the school, each student has a student ID number that's unique, and you could just put that student ID number in every table, right? And then you could just say, for the row that starts with this student ID, this is their address? Or is that not how it works?
So that's not how it works for a relational database management system. But again, if we wanted to, say, okay, Elda here has a student ID of 2. Whenever we add any other record that depends on pointing to a student record, we would just say, okay, give me, the student ID would be 2 to point to Elda. And that would be true no matter what, because only one student has the ID of 2. And not every column is going to have a foreign key necessarily. Like addresses doesn't have a foreign key because the student is the one that points to it, not vice versa. But also some records may have many foreign keys. Kind of all depends on how your tables are interlinked with one another.
And if you wanted to pull up a list of all of the like all of the Chicago addresses in this particular class or something, can you do that easily?
Yeah. As you can see, for example, we have one student in Chicago, one student in Joliet. So we could say, essentially we would say the line would be select all from addresses where city equals Chicago. And that would go through this address table and give us every record that matches that.
Okay. And if you wanted a list of the students who live in Chicago, then you would say from students, list all entries where address, or what would that look like?
So it looks something like select all from students where student.address, or you do a join. What's called a join, and joins are a little more complicated. I don't know how to do one off the top of my head, but you would join the students column and the address table. You would say, okay, join where the address ID equals address.id. So that, creates this connection here. And then you would say where address.city equals Chicago.
Okay.
So in kind of more Pythonic terms, I would say, I would be looping through students and say where student.address.city equals Chicago.
Okay.
So that, and you'll find that there's ways to translate Python into SQL and vice versa. So
Thanks.
you won't necessarily have to, you'll be doing a lot of SQL tomorrow and today, but then after, eventually you won't necessarily have to write the SQL directly yourself because people have written layers of abstraction to kind of translate that for us.
Thank you.
But it's still important to know what's going on in the background. So good schema design improves your data's integrity. So careful use of database constraints, such as column uniqueness or not null, will protect you from situations like this. So this will allow you to say, you can't have 2 records called james@example.com. You can make it so that each column has to be unique. So you can say every email has to be unique as well as every ID. So because if we don't do that, we don't know which password to check when James logs in.
So is this how websites, when you try to create a username and it's already taken, it's because it looks at a SQL database and it does that integrity check?
If it uses a SQL database, then yes, exactly. There are there are other things out there. A very popular one right now is NoSQL, which is, literally it just doesn't use SQL. But yes, that is what's happening, is that anytime you try to log in, and it'll automatically check against its database to see if that email is already in use. All right. So I guess before we talk about queries, because this is this whole thing, what questions do you have about schemas and SQL tables? Okay.
Just
Yes.
a quick question. So there is only one schema on your database, that's it?
Yes. So think of your schema as the blueprint for your database. So you won't, if you're designing a building, you might have many versions of the same blueprint, but it's still, you only want one master blueprint at the end of the day, right?
Yeah.
So yeah, that's what a schema is. Your schema is your blueprint. It's, deciding where things go and why.
Is there a limit for the tables that you can create?
Probably, but it's very, very large. If you're making like a Facebook or a Twitter or a LinkedIn, I'm sure, I don't know if they use SQL databases. I would need to check. But if they do, they must have dozens, if not hundreds of columns, of tables, I should say. Because, looking at Facebook, you'd have a user, that user has photos, that user has posts, that user has likes and comments, that user has pages, that user has groups. It's, it's huge.
At my last company, we had hundreds of tables. Like our company was like 15 people. So Facebook has probably thousands upon thousands of different databases.
Yeah.
With,
Yeah, and I just looked it up. Facebook does use a MySQL database. So yeah, so they
is a relational database one that can read multiple tables and just kind of aggregate your results by reading multiple tables?
Exactly.
That's what relational database is.
Yep.
Whereas if it's a non-relational database, it's just one table.
Not necessarily. There are many other ways to do things, but often, like what we were talking about earlier with the hierarchical thing, it's in that case that was a file-based one, where essentially you've got like a big filing cabinet of records that you can go through.
Okay.
Yeah, essentially like a NoSQL database, something like Firebase or MongoDB. It looks like a gigantic hatch.
Yeah.
And yeah, it's just a different way to query. It's harder to relate different data to one another.
Yeah, but if you only have just one type of record, then that would be really good. So like at one of my previous jobs, we would have our students make like a chat app, and we used Firebase for that because Firebase is fast and all you really need to keep track of is messages. And so it's very simple it's simple and fast, but you didn't have to worry about, okay, if how do messages relate to X? How do messages relate to Y? Because there's only, all that really was messages and users.
Yeah. Generally, NoSQL databases are a little bit quicker to query.
Yeah. All right, let's talk about queries. So structured query language, so queries are important about this. All commands are lumped together and called queries in SQL, including commands that don't necessarily query for anything, but instead do something. So we talk about query, it doesn't necessarily mean asking a question, it can also mean creating a table. It's an example of a query. So the most often you'll be querying a table with the following commands. So there's select, which retrieves rows that match a query. Insert, which creates a new row. Update, so that updates a row that already exists. And delete, that deletes a row. So the most common query type is a select query, which allows you to retrieve matching records from rows from the database. So select all from students means give me every student and give me all of the information about every student in this database. So it retrieves the ID, the first name and the last name of Tiana and Elda, both rows of our database. So that star there just means everything. Select all of the data. We can also specify what columns we want by saying you can just get the ID and the first name. So ID, first name from students, just returns the ID and the first names while ignoring the last name. Often you only want to retrieve records from students that match a condition. So if we just wanted Elda's ID and first name, we would say select ID and first name from students where ID equals 2, or where first name equals Elda, but there might be more than one student named Elda. So that's why we use the ID instead. So the where operator is very useful. There are many conditions that it supports. So there's a few. So equality, whether or not a column name is equal to a value. You can also use inequality, which can be represented as bang equal, or this symbol right here. You can use greater than or less than values, or greater than or equal to. Between will allow you to check if it's between two values. You can present a list of values by using in. And if you want to match a pattern, you can use like. So if you wanted to say, where something, like if you wanted all your email addresses where it's Comcast, you would say, select all from emails where email address is like, and then you'd probably do star@comcast.net. Where email address like star.comcast.net. So we have some examples here. So you wanted, select all from students where first name is Andre. This would give you every student whose first name is Andre. This would give you select all from enrollments where the grade is not equal to A. So this would give you all of your B, C, D, E, and F students. You could get all your classes where credits are between 3 and 4. You can select all from enrollments where the grade is either A or B. So in A or B. And then you can also use, get a little more fancy with it and say select all from classes where the name has art, like art. So where art is in it somewhere. And the credits are greater than 3. So the AND operator lets you add extra conditions. Any question about selecting from a database?
Does the percentage sign mean something?
Yes, that percentage sign is what's called a wildcard operator. So we say where name is like art %, we're saying where the name has art and then some characters afterwards. So that would give us art 1, art 203, art 5, art 50, etc.
Hey, Noah, are you
Yes.
also able to put that wild card before the word art?
Yeah, absolutely. If you wanted, if you were looking for every 101 class, you'd probably write it as wildcard 101. So that would give you art 101 and math 101 because we're saying some number of characters followed by 101.
Thank you.
No problem. All right, let's talk about inserting records. So new records are inserted in a table by specifying the table name, the columns, and the values we wish to insert. So you wanted to enroll a new student, we would say insert into students, and we would say, okay, we're inserting the first name, last name, and birth date. And the values we're inserting are Michel, DuPont, 1982, 02, 11. So these specify which columns you're inserting, and the order needs to match the values that you put in. So that's pretty much it. Again, you don't necessarily need to include every column in a table because sometimes some columns might be optional. So you can always say, I want a row and I only want the first name and last name and birth date is optional. And you just say Michel DuPont and leave this last one blank because you wouldn't have birth date here. That's really all there is to it. It doesn't get very complicated. It's just saying insert into students. Here are the columns I want to do. Here are the values that go into those columns. Any questions about inserting new records? Right. Updating works much the same way. It allows you to change the values of a column. The new column value is applied to all rows that match the where conditions. So this is one you do have to be kind of careful with. So if you wanted to update an address, you'd say update addresses, and then you would set line 1 equal to that. You can change the zip code equal to that. So that would update whatever's already there. But the where says, okay, which one am I actually updating? So if I said, where city equals Chicago instead of ID equals 2, that would update every record whose city is Chicago with a new line 1 and a new zip code. And deleting just says delete from addresses where ID equals 2. So again, it'll delete every row that matches the where conditions. So using the ID is usually the best way to do that because the ID always has to be unique. So you won't accidentally delete anything you didn't mean to. So if you fail to include a where condition, you'll affect all rows in a table. So if you just did update addresses without saying where, it would update everyone to 200 Church at zip code 60010. And if you delete from addresses without saying where, it'll delete everything. And you do not want to be that guy. Don't delete the entire database, please. Great. Any other what questions do you have about SQL?
I would assume there's no undo, right?
Sorry, could you repeat that?
I would assume that there's no undo.
I don't know. There might be, but I wouldn't chance it.
Right.
All right, so I know I just threw a lot of information at you. So I don't expect you to learn all of this today. So if you look at our challenges, we actually have 8 challenges to be done over the next 3 days. So take these at your own pace, just do them in order. So you'll be starting with SQL Basics, which has everything that we just kind of went through here. You know, select, insert, update, delete, create, drop. And you'll be using Postgres to create your database. And I believe we set up Postgres during our install fest on day one, right?
Yes.
Yeah.
If it
So-
doesn't automatically start right away, let me know.
Yeah. Yeah, Postgres can be a little finicky sometimes. So if you have trouble accessing PostgreSQL, yeah, contact Tom or myself, and we'll get you set up. So yeah, you'll start with SQL Basics, and then move on to schema design, schema, SQL, schema modifications. So again, you have 3 days to do all of these. You probably won't have much time tomorrow though, because that's our SQL workshop. So yeah, after tomorrow, you're going to be, if not experts at SQL, you're going to know more than much more than you do today. It's a lot of good information, but it's presented extremely well, so you'll know so much.
Quick question, Noah.
Yeah.
Because tomorrow is a pair programming day. Does that mean these assignments, like, is the workshop going to be our pair programming exercise, or are we going to utilize whatever assignments we haven't completed yet?
So the workshop is going to be, like, that's entirely run by Jake and Jack. So you're not really going to be doing much pair programming tomorrow unless Jake and Jack want you to. Because otherwise, yeah, that's going until 5 o'clock. So essentially, no, you won't be doing pair programming for these because you won't be pair programming today. You won't have time to do it tomorrow. And then Wednesday is not a pair programming day.
Got it. Thank you.
Great. Any other questions?
Are we still forking the repo as normal?
Yes.
Okay.